So now, test of parallel and counterflow heat exchangers for MLab 2. So ito yung first is the log mean temperature difference. So heat exchangers na discuss niya na to sa heat transfer. So to design and predict the performance of a heat exchanger, it is essential to relate the total heat transfer rate to quantities such as the inlet and outlet fluid temperatures as the overall heat transfer coefficient and the total surface area for heat transfer. Two such relations may readily obtained by applying overall energy balance to the hot and cold fluid as shown in figure 1. Consider this is the heat exchanger. Overall heat balance for hot. This is the hot one and the cold one. So ito same flow. So ano siya? Parallel. So ito yung mga masses and I is the enthalpy. Dito gamit natin is H. Okay. So yan, THO, temperature on hot side, out. Okay. In particular, if Q is the total rate of heat transfer between the hot and cold fluids and there is negligible heat transfer between the exchanger and its surrounding, as well as negligible potential and kinetic energy changes, application of the steady flow energy equation gives Q is equal to M dot times H I minus H O in and out, and Q is equal to MC times HC out minus HCO. Cool. Where H is the fluid enthalpy. Yung hot, lalabas siya ng malamig. Kaya mas mababa yung HO isa sa HI. Yung cold water naman, iinit. Kaya yung out niya mas mainit kaysa HI. Okay? Now, the subscript S and C refers to hot and cold fluid, where I and O designate the fluid inlet and outlet condition. If the fluids are not undergoing a phase change and constant specific heats are assumed, this expression reduces to Q is equal to MHCPH times TH minus TI, HO, and Q is equal to MCCPC plus TCO minus TCI. So, dito tayo mag-concentrate sa without change of phase. Pag may change of phase, ibig sabihin, yung isa steam, isa water. Okay, where the temperatures appearing in the expression refer to the mean fluid temperatures at the designated location. Mean. Note that equations 1 and 2 are independent of the flow arrangement and exchanger type. Any type of heat exchanger. Maraming klase ha. Huwag natin i-discuss kasi may separate topic yan. Another useful expression may be obtained by relating the total heat transfer rate Q to the temperature difference between the hot and cold fluids, where delta T is the temperature of hot minus the temperature of the cold. At this point, TSI minus TCI. Okay, at this point naman, TCO, HCO. Yan, may difference siya. That is, times mo yung value niyan, yung heat transfer coefficient, so makuha mo yung heat transfer. Such an expression would be an extension of Newton's law of cooling, where the overall heat transfer coefficient Q is used in place of single convection coefficient H. However, since delta T varies with position in the heat exchanger, it is necessary to work with a rate equation of the form Q is equal to UA delta Tm. Delta Tm is an appropriate mean temperature difference. Equation 4 may be used with equation 1 and 2 to perform heat exchanger analysis. So, tatlo na, di ba? Dito kasi makakuha mo yung dimension ng heat exchanger. Before this can be done, however, the specific form of delta T must be established. Stop muna tayo. So, ito. Pag-change ko lang yung symbol. Now, next, pag-establish ng delta Tm, dito na papasok yung counterflow and parallel flow and the cross flow. Cross flow, hindi na yata abot dito. Alam nyo na yun. So, dito lang tayo sa counterflow and parallel flow. The parallel flow heat exchanger, so the hot and cold fluid temperature distribution associated with parallel flow heat exchanger as shown in figure 2. So yan. Parallel flow, so ito na yung nakikita nyo. Same ang direction niya. The temperature difference delta T is initially large but decays with increasing X. Yung X yung distance ng yung tubo. Ito yung sa yung tubo, ito yung sa shell. Yeah. Basta ito yung isang yung transfer medium niya. Ito yung plate, ito yung transfer area. So, mas anong distansya niya. Pag nag-ano na siya, mas lumiliit yung delta T. Approaching zero asymptotically. It is important to note that for such an exchanger, the outlet of the cold fluid never exceeds that of the hot fluid. In figure 2, the subscript 1 and 2 designate opposite ends of the heat exchanger. This convention is used for all types of heat exchanger considered. For parallel flow, it follows that H sub I, THI is equal to TH1. Ito. And THI is equal to TH2, etc. and so on. Now, the form delta Tm may be determined by applying an energy balance to differential elements in the hot and cold fluids. So, di na kailangan dito yung derivation na pag-mention lang. Its element is of length delta x and heat transfer surface dA is shown in figure 2a sa taas. The energy balances and subsequent analysis are subject to the following assumption. 1. The heat exchanger is insulated from its surrounding, in which case the only heat exchange is between the hot and cold fluids. Number 2. Axial conduction along the tube is negligible. Then potential energy and kinetic energy changes are negligible. The potential specific heats are constant. 5. The overall heat transfer coefficient is constant. Yan yung mga assumption. Now, the specific heats may of course change as a result of temperature variation. And the overall heat transfer coefficient may change because of the variation in fluid properties and flow conditions. Dito papasok yung trial and error nyo. Makita sa mga transfer book nyo. Talaga trial and error siya. Pinukuha nyo yung specific heat sa table, sa kaibang properties. So, hindi na nagbabago yung pinasyo mo, so that is the final na. Okay? However, in many applications, such variations are not significant. And it is reasonable to work with average values of CPC, CPS, and U for the heat exchanger. Okay, the appropriate average temperature difference is log mean temperature difference, delta T Lm, which is accordingly, we may write Q is equal to UA delta T Lm, where delta T Lm is equal to delta T2 minus delta T1 over ln of delta T2 minus delta T1 is equal to delta T1 minus delta T2 over ln of delta T1 over delta T2. Kayo na bala sa equation number. Okay? Ang symbol nitong is LM, ang delta T Lm is also LMTD or theta M sub M. Okay. Remember that for the parallel flow exchanger, delta T1 is equal to equal na equal sa katatlo yan. Linya. TH1 is equal to THC1 is equal to TH1 minus TC1. And delta T2 is TH2 minus TC2 or THO minus TCO. Okay. So, yun yung sa parallel. Now, sa the counterflow heat exchanger naman tayo. Andito yung sa figure, di ba? Papunta sa left, papunta sa right, papunta sa left. So, this now, THI, TCO. Yan. THO, TCI. So, yan ang form niya. Temperature distribution for a counterflow heat exchanger. Lalagyan yung gagawa ng ganyan. So, in contrast to the parallel flow exchanger, this configuration provides for heat transfer between the hotter portion of the two fluids at one end, as well as between the cold portion of the other. For this reason, the change in the temperature difference delta T is equal to TH minus TC. Diba? So, with respect to X is now as large as it is for the inlet region of the parallel flow exchanger. Note that the outlet temperature of the cold fluid may now exceed the temperature of the hot fluid. Equations 1b and 2b apply to in a heat exchanger and hence may be used for the counterflow arrangement. However, for the counterflow exchanger, the endpoint temperature difference must now be defined as delta T1 equals TH1 minus TC1 is equal to TSI minus TCO. And delta T2 is equal to TH2 minus TC2 is equal to THO minus TCI. Yan sa counterflow heat exchanger. Note that for same inlet temperature and outlet temperature, the log mean temperature difference for counterflow exceeds that for parallel flow. Delta T LMCF counterflow is equal to greater than delta T LM parallel flow. Hence, the surface area required to effect a prescribed heat transfer ratio is smaller for the counterflow than for the parallel flow arrangement, assuming the same value of U. So, kaya common yung counterflow. Mas maliit yung area. Also, note that TCO can exceed THO for counterflow but not for parallel flow. Kaya mas common yung counterflow. Now, special operating conditions. Okay, now special operating condition. It is useful to note certain special conditions under which heat exchangers may be operated. Figure 4A shows temperature distribution for a heat exchanger in which the hot fluid has a heat capacity rate of CH equal to MH CPH, which is much larger than that of the cold fluid. CHM is equal to MC CPH. For this case, and CH is greater CC or a condensing vapor. Same direction niya, pababa. For this case, the temperature of hot fluid remains approximately constant throughout the heat exchanger, while the temperature of the cold fluid increases. So yan, into any direction niya. Condensing. And the same condition is achieved if the hot fluid is condensing vapor. Condensation occurs at constant temperature and for all practical purposes, CS approaches infinity. Conversely, in an evaporator or boiler, figure 4b, it is the cold fluid that experiences a change in phase and remains at a uniform temperature. C approaches infinity. Yun na kaya, diba? So, this is for evaporating. That pardon. So, nag-evaporate to, so bumababa yung temperature na. Yan. The same effect. So, ito naman equal yung CC is equal to CH. So, the same effect is achieved without phase change if CH is greater than C equal to CC. Now, note that with condensation or evaporation, the heat rate is given by equation 1A or 2A. The third special case, figure 4C, hindi, less than. Involves a counterflow heat exchanger for which the heat capacity rates are equal. C is equal to CS. The temperature difference delta T must then be a constant through the exchanger, in which case delta T1 is equal to delta T2 is equal to delta Tm. May mga case na ganyan. Okay? So example. Counterflow concentric tube heat exchanger is used to cool the lubricating oil for a large industrial gas turbine. The flow rate of cooling water through the inner tube, sabi concentric may tubo, yung tubo, may tubo sa loob. May ibang tawag dyan is tube in tube. Eh, heat exchanger. So di is equal to 25 mm is 0.2 kilogram per second, while the flow rate of oil through the outer annulus dissolved is equal to 45 mm. Alam niyo na yung annulus, di ba? Is 0.1 kilogram per second. So the oil and water enters at temperature 130 C. Counterflow siya, respectively. How long must the tube be made if the outlet temperature of the oil is to be 60 C? Ayan, hanapin nyo yung haba ng tubo. So given lubricating oil, that H is 0.1 kilogram per second. Kasi ito yung hot side. TSI is 100 C, TSO is 60 C. Outlet temperature. So water is the cold side, which is 0.2 kilogram per second. TCI is 30 C. Dissolved is 25 mm or 0.025 meters. Dissolved is equal to 45 mm is 0.045 meters. Required is the length of tube. Solution, reference natin yung mga value na is fundamentals of heat and mass transfer by Encopera et al. Ba? Makita nyo naman sa internet yung book. So, unused engine oil at TH is equal to 1 half of average 100 plus 60. Yan, di ba? Average is 80C is 353 Kelvin. CP is equal to 2131 joule per kilogram Kelvin. May table yan at 8353. Nu is equal to 3.25 times 10 negative 2 Newton seconds per meter squared. K is 0.138 Newton per meter Kelvin. Water at TC is equal to 35C. So, para makuha natin yung this is the average ng TC. So, nag-try tayo ng average ng 35. Si 60, ang niya is 30. So, matataas pa siya. Di ba? So, taasan mo ang trial mo average. Hanggang sa solvin mo yon average ulit. CP is equal to 4178 joule per kilogram Kelvin. Nu is 725 times 10 exponent negative 6 Newton second per meter squared. K is 0.625 Newton per meter squared. PR is equal to 4.85. Itong mga symbol na ito, PR, Reynolds number, Grashof number, huwag niyong i-italics. Required heat transfer, Q is equal to MHCPS times TSI minus T subaw. Given kasi lahat yan sa mga kuha mo. Q is equal to 0.1 times 2131 times 100 minus 60 is 8524 watts. Also, Q is equal to MC times CPC times TCO minus TCI. So, TCO is equal to Q over MC, CPC plus TCI. Substitute values. So, 8524 over 0.2 over 4178 plus 30 is 3040.2. So, accordingly, use of TC35 to evaluate the water properties was a good choice. Diba? 40.2 plus 30 divided by 2 is approximately 35. So, good. For heat exchanger length, Q is equal to UA delta T, so LM. So, delta A is equal to mu DIL. So, delta T LM is equal to TSI minus TCO minus TSO minus TCI over ln of TSI minus TCO over TSO minus TSI. Substitute values, magiging 42.2. Then U is equal to 1 over SI plus 1 over S. So, neglecting thickness ng tube at fouling factor. Consider as clean. Okay? Water flow through the tube solving for SI. RED is equal to 4 MC over pi di nu is equal to 4 times 0.2 over pi times 0.025 times 725 times 10 negative 6 is 14,050. So N sub UD, Nusselt number is 0.025 times RA sub D exponent 4 over 5 and PR 0.4. 0.82 kasi siya heating. Kapag heating, di ba? So NU is equal to 0.023. Oops. This is 0.023. Okay, wait lang. N tuloy. So HI now is NUD times K over DI is equal to 90 times 0.625 over 0.02 is 2250 watts per meter cubic. So, remember yung mga equation na to, heat transfer, heat transfer. Flow of oil to the annulus, D sub S equal to D sub O minus D sub I is 0.045 minus 0.025 is 0.02 meters. Now, Reynolds number is rho density, times dH, mu, or rho times d sub o minus d sub I over mu times 4mh over rho pi times d sub o squared minus d sub I squared. This is the uh, flow rate, volume, velocity. The area ng annulus over 4. Tapos ito yung hydraulic radius. Okay? So, RAD is equal to 4mh over pi times d sub o plus d sub I mu is equal to 4 times 0.1 over pi times 0.045 plus 0.025 divided by 3.25 times 10 to the power negative 2 is 56. And the annulus is therefore laminar. Table 8.2, reference with DI over DO is equal to 25 over 45 or 0.56. So NUI is equal to H or DH over K is 5.63. Okay? Table 8.2, wala dito sa slides, kundi andun sa libro ni Incopera. So H over is equal to NUIK over DH is 5.63 times 0.138 over 0.025 equals 338.847 watts per meter square Kelvin. Now, the overall coefficient of heat transfer is 1 of U is equal to 1 over 1 over HI plus 1 over HO is equal to 1 over 1 over 2250 plus 1 over 38.847 is 38.188 watts per meter square Kelvin. Now, the length of tube from Q is equal to pi DILU delta TLM, L is equal to Q divided by ito, pi DILU delta TLM, is equal to 8524 over pi over 0.025 divided by 38.188 divided by 43.2. So, itong dalawa ang importante mong makuha. Delta TM and U. So, the length now is 65.8 meters. So, check mo na yung value. Okay? Yung nagamit mong equation dyan. So, this is now the end of this topic. So, dito yung figure niya. Diba? Parallel flow and counterflow. Close.